Okay, we're going to try this again. I think I need to just not answer the telephone. All right, we're going to be looking at computer processing where it relates to digital images, and specifically this first one here is concentrating on image pre-processing, and then the second one here, hopefully I get this thing done, is going to be post-processing. And all of this information is located within Chapter 7 of your text, the Farber text. That's the one I'm kind of concentrating on. And as I've told you, you're kind of getting sort of a sprinkling of Quinn Carroll's materials too. I have to tell you, I just wish you guys had been in on some of the ones that he gave, because I think you'd find it so much helpful right now. Not saying that you hadn't been there and had done good stuff and things like that, but this, what can I say? All right. By definition, where your pre-processing is concerned, okay, keep in mind what we've done up till now is talk about the data, the electronic signal, okay, has essentially been gathered up by the detectors and has been sent in what we hope is a coherent manner, okay, along the switches to the analog to digital converter, okay, and then to the processor. So that's where we are right now. So the raw data, okay, by definition, and this is something we talked about in the last video, the raw data is very, very sensitive to changes in the attenuation values, okay, of the radiation, okay, whether the radiation has been transmitted through or whether it has been attenuated to some degree or another. As a result, the raw data there, okay, has the capacity to display a lot of differences. In other words, we're talking about something gray, okay? Now, we don't really necessarily want that, okay? What we want is something that is an image that we like, okay? So a lot of what's going on here in the pre-processing is geared towards creating an acceptable digital image, okay? That's what's going on. You're taking the raw data and you're ultimately going to produce an image. Now, it may turn out that you don't like the computer's idea of an acceptable image, in which case you have the capacity to post-process the image, where you're now essentially, and I like Carol's word here, which is refine the image. Okay, if you think about it, what can you do to the displayed image? You can zoom it, you can reverse it, you could do subtractions on it, you can sharpen the edges, do edge enhancements, you can essentially smooth it, and things like that. All those things have been done to the digital image that has been given to you by the computer. Okay, so in essence, we're looking at correcting the image correcting the image data, okay, to make it produce an image that looks okay. Post-processing is taking that image there and then kind of refining it, because you want to make it a little bit better. Okay, now, pre-processing, one of the things that we kind of have to keep in mind, and this doesn't matter whether we're talking about a CR flat panel detector or frankly a PSP plate, is that they are not 100% no holes barred uniform. Okay, it is possible, for example, for a TFT to be dead, okay, and not sending any data at all. Or there may be issues with noise that is coming through the switches. Okay, if you're talking about a CR plate, these plates have crystals in them. Okay, by no means can we expect that the crystals are evenly distributed, okay, on the plate, nor are they perfectly the exact same size. Okay, both of these things are potential issues. By the way, we don't even necessarily hold that the plate has the exact same thicknesses from one point to another. Okay, those are things that can interfere with the responsiveness of the system if you get right down to it. The computer has to correct for this. Okay, now, all right, we talked about this already. This is what I found was kind of interesting, because the CR plate part here, the dark noise, I get it, that's not hard. If you leave a plate out, we leave those plates out, they don't get used that often. One of the things you might have noticed yesterday that I did was that I cleared that 14 by 17 before I gave it to you to make exposures. That's because I recognized that there was background exposure on it that we wanted to clear out. All right, we call that dark noise. Now, you can sometimes see the dark noise on the initial image, but the lovely thing is that for the most part, okay, the processor has the capacity to write it out, so that ultimately the image that is displayed doesn't display this dark noise. But it's not to say that the data isn't there again. It's just the computer is doing its thing. Now, the thing I don't 100% understand with a lot of this, it's not entirely clear to me, is what this dark current is when you're talking about a flat panel detector. Okay, residual current after exposure, to me that translates into afterglow or lag. And what those mean is that there is signal still being sent even though the X-ray beam has terminated. Anything that's being sent after that point obviously is unwanted, and that's precisely what we're talking about as an issue here. All right, now they made some kind of an exposure here. Maybe they left it out for a week, I don't know. One of the things you can see here is that the responsiveness of this particular plate definitely varies. You can kind of see how, obviously there's been a lot less, I guess you would say, a lot more transmitted beam here. Even as you come down here, there's a lot less. Or you could say, if you'd like the opposite, there's been greater attenuation of the beam down here than there is in these central portions. The computer pre-processes this out. Okay? All right, here's another issue related to field uniformity. And it's really not anode heel effect per se, but certainly looks like something we would call anode heel effect. But you can kind of see what's happening here in the fact that you've got greater transmission of radiation here, certainly that you have down here. But what's interesting is it's a uniform gradient. Okay? Something that's as predictable like this is probably a whole lot easier for the computer to adjust for than the previous one right here, where it seems to be sort of completely chaotic. It's random. All right, now, what happens at this point? Well, one of the pictures that I showed you, the animation, was showing you that the Dells was sending information that in turn corresponds with the pixels at a particular point. Okay? So everything has its position. Well, the computer has to know a few things about this, and one of the things it has to know is that where your actual image data begins and where it ends. And it doesn't matter if we're talking about CR or DR. Bottom line is it needs to know what part of the total receptor field it actually has to work on. Okay? Now, with computed radiography, we have the potential that we do not have with DR. Specifically, we can put multiple exposures on a single plate. Okay? And again, you've done these things here just a bit. And the processing software has to basically identify these changes. Okay? So we've got basically an area here of high transmission, and then all of a sudden we have nothing. Then we go right back immediately here into another area of high transmission. The computer has to adjust these things and understand that it's looking at two different images. I talked to you one time about the fact that I did a finger, 1, 2, 3, on an AVCA-based CR, and the middle one came out completely and totally wrong. It probably was an example of a segmentation error where it simply did not, it understood the two on the outside but did not recognize that third one. And in turn what it essentially tried to do was to average everything in there, and that's why we ended up with a middle picture that was French fried. That would probably be a segmentation error. Okay, now this sort of relates to what I was talking about here, where these images begin and end. Okay, so you could call that a field recognition error that leads to a segmentation error, for example. One basically causes a problem with the other. In general, okay, the computer would like to know where 3 of the edges are. Sometimes it'll work with 2 and you will be just fine. Okay? Sometimes it won't. It sort of depends on how it's sort of aligned. But it likes to have 3. In a perfect world, it would have all 4 collimator points. So, when we talk about this stuff, again, about collimation versus croptic, there are other really, really valid reasons why you want to give that poor computer borders. Okay? So, the computer and the CR system is going to detect those kind of really dramatic changes in the blackening on the image here. Okay? And it has to be distinct for that to actually do here. So a couple of things that can happen. How about if you had lots and lots of scatter radiation? Okay? If you think about it. Then the computer cannot identify the edges. So what is it going to do? It is going to take the entire field and process that. And when it processes that, then it tries to go to work and average everything out so it has a uniform and expected density. And hence we end up with these interesting images that are either radically light or radically dark. And you have produced examples of both. Okay? You remember this picture here? This is kind of a classic example of this, where they took a receptor and they were x-raying a newborn baby's arms bilaterally. The images, as you can see here, we've got 4 borders, but notice the way that they're oriented in kind of a funny sort of way here, and the computer simply couldn't handle it. Now, let me point out, this was a long time ago, and the ability of these CR systems to detect and correct for segmentation errors has gotten a whole lot better. Okay, but what happened here, guys, is that the computer said, all right, we don't know what this is. We are calculating the information for all of this. This is segmentation error. So all of this unexposed area here is averaged in to the exposed area, and really it's compensating here. So we end up with kind of like really, really dark images. Now, can you fix those? If you could go to work and reduce the field, and here's where the problem gets to be. Okay, because if you go to work and apply field, actually here, in other words, you tell the computer, limit yourself to this specific area, maybe you could, if you went back and you pre-processed it again, giving it artificial borders. All right, if the computer detects no edges, like I said, it's going to include the entire field, and like I said, that's never a good thing. Unless you are utilizing a system, a lookup table, that it's expecting no edges. And an example of that would be a chest x-ray or a KUB. It's expecting you to use the entire 14 by 17 with both of these. So if it doesn't get these edges, it's okay with it. But on the other hand, if you are doing something like a lower leg or a foot, it's expecting edges. So that's where you can run into those kind of problems. Okay, here's an example where you've got segmentation error. The picture doesn't look god-awful, but the problem is that it doesn't really get the fact that there's 4 of them. See how you've got this kind of darkened area here? What it did is it took everything, all right, and it calculated based on everything. So what you end up with is uniform kind of darkening of the whole, or graying of the whole image. It's poor, okay, and it's happening because of that. That's a segmentation error. Please remember again, it only happens with CR. Okay? All right, but that doesn't mean that you can't have exposure field recognition type of errors with both of these systems. Okay? So, in a sense, EFR can lead to segmentation error with CR. But that doesn't mean that you can't have the same thing happen if it is only one image on the receptor. In this case now, CR and DR are similar. If you have some kind of a really wonky setup where you've only got one field on there, one exposure field, but it's in there in such a way that the computer cannot make heads or tails of it. Okay, let me give you an example if I possibly can. I tried to draw some of these things on the board. Okay, but all right, there is your image. Here's your field. Okay, the 14 by 17 if it's like. And you've x-rayed something and it's up here. So this is where it is. Okay, the computer is not going to understand that. And what it'll do then is it will take all of this information, all of this unexposed area, and it averages into here, and what you're going to end up with is a dark spot. Okay? So doing this is part of what's called your histogram analysis. Now, we talked a little bit about histograms in class. I had you actually drawing histograms and things like that. By definition, a histogram is a graphical display of the frequency of occurrence of something. Okay? In this particular case, we're talking about how often a particular pixel, if you'd like, okay, has a particular intensity. Okay? So it's a distribution of those things here. Okay? What we want to do is define the edges. Okay? And if we find the edges, then we know where to start the actual processing. The other thing here is that another thing happens. I probably should not have put this directly here. If you have defined edges and you have automatic masking turned on, it'll go to precisely that. All right? So what happened over here with this particular image is it's a little bit off, as you can see here, and the computer had its problems with that. Okay? What they have done is they put in a certain amount of masking in an effort to try to go to work and tell the computer where the edges are, and it still ended up being problems. And the thing that can tell you that you got problems is the fact that you got all of this stuff down here and all of this stuff up in here and all. Okay? Now, if you go in there and you physically manipulate the mass to bring it to the actual exposure points, and then you turn around and reprocessed it again, you can see what basically happens. This is the exact same thing. Okay, these are both the same image, taken with the same exposure factors. The difference is a question of basically giving the computer the information that it actually needs to process it properly. All right, so let's get back to histogram analysis. All right, this, by definition, is how you detect the edges and then go to work and assess the data that are between the two edges. Okay. I like that. I like Carol's definition just as much. You're looking for landmark changes. Jump from no exposure to exposure, all right, on the histogram. That is histogram analysis. When you get those landmark changes, you mark them. And we mark them with these volumes of interest, or the VOIs. Okay? So when we look at something like this, and I'm going to go through, I'm going to pass this because we've already talked about it. Okay? All right, let's go. Now, we talked about this in the distribution of these pixel values and all. Okay, so here we'll start. There is a picture of a wrist, a broken one, incidentally, and you can kind of see where the actual borders are. Okay, take my word. This is actually, so this is the collimated area here. How do we go to work and determine that on a histogram? Well, what the computer does is it looks at everything from here, and at the same time it's looking here. So it's taking from the total amount of data and it's looking basically towards both sides. With a wrist, it is expecting that there's going to be areas there of unattenuated radiation, transmitted radiation. What we're talking about is all this stuff here. Whoa, sorry about that. Okay, and over here. Okay, that's what we're talking about. That's what you are reading with this part right here. Okay, right there. Why is it expecting that? Well, it's because it's an extremity. There's always areas there where you anticipate you're going to have unattenuated high-value radiation. What I'm presupposing with all of this is the area for black. That means, of course, on the opposite side of the continuum, this is white. Okay? So the computer is looking this way, the computer is coming in this way. When the computer reaches the first point where there's a big jump in the attenuation values, okay, or the beginnings of a jump of the attenuation values, okay, in essence, what we're doing here is now all of a sudden we're basically shifting from white, we're heading towards grays, and something actually occurs. All right? It marks it. At the same time that's happening, it's looking at the values over here. The computer has been told to ignore the first bump, okay? Because this is not all that important out there, okay? So it ignores that first bump. So when now we end up with this point where it's starting to go back up again, the computer knows to mark this point. This is skin, okay? So everything else that's in between here is the data of interest. Okay? That's the data of interest. This is what the computer wants to process. Now, if the computer cannot recognize these borders, that's when you end up with these errors that we've been talking about. Okay? So kind of in the background there, this is really what it kind of gets down to. We've got white on one side of the continuum, you have black on the other side of the continuum. We expect this is going to be outside the exposure field. In other words, this is the place where we've collimated. We don't want to add that in. In fact, I was just telling you why you didn't want to add that in. On the other side here, okay, this is actually going to be actually inside the exposed field, but it's outside the anatomy. Okay, we're expecting this when you're talking about extremities, because we don't collimate right to the skin as a general rule. Okay, but we basically have told the computer to ignore this. So VOI 1 to VOI 2, that's where the action actually is, and this is good for an extremity. Okay, here's just another one there. I just pulled this off the net. It's one of those deals here. Okay, just keep in mind what's going on is the fact that it's looking from point here, and it's looking to point here, and then it knows how to do a histogram analysis. Okay? When it gets that information, when it recognizes where the borders are from your data, okay, keep in mind, as I told you before, there is a pattern, okay, that is programmed into the imaging software, okay, that is the ideal for each of these positions and things like that. Okay, the job of the computer essentially is to take the ideal, to take the information from yours, and to essentially merge them together to create a coherent image. This is one of the reasons why you guys don't have nearly as much problem with exposure. Okay? Alright, now, this is talking a little bit about things that could potentially happen because of errors. And the computer can certainly do errors. And the one I classically used was shields, but guys, it could be something, for example, like a metal hip replacement that does it. We already talked about the fact it's because you could have something wonky where it doesn't really quite understand where bright versus dark is. The point is that if your pattern, okay, does not really measure up, whatever, match, okay, the data that's already been programmed into the system, you can end up with histogram analysis. Barium can do something like this unless you set up a barium-based algorithm, okay, which it actually happens to be. Okay, I have to stop again. Hang on. Yes, ma'am. I did. I've already sent out. I called Adrian because he's the class president, and because he's the only one whose phone number I actually had on my phone. And I asked him to go to work and send the information out, and then I turned around and I sent the whole thing out as an email to everybody. What I am hoping is that he'll go to work and get the word out fast enough, hoping he gets it, to do it today. Okay? The sooner the better. And yeah, so that's where we are for the moment. Yep. Not a bad day. What are you doing? Okay. I've got a live video thing going on here, so I probably need to get off the phone. I haven't quite figured out how to shut this thing off because I'm working on a, what do you call it? I only have access to this for a month. I haven't paid for it yet. A trial. So it's kind of limited in its editing. Ciao. Yeah. Mm-hmm. You and me both. Because you said, did you even look yet? And I said, well, maybe I better go check my email. Alrighty. Take care. Bye. Alright, sorry about that, guys. Alright, let me kind of point out. Let's say, for example, let's leave the barium aside. Let's talk about this shield. Okay? You have a 14 by 17 size receptor. We're going to put this thing here, lengthwise. By the way, this might be an argument for you to do everybody crosswise. Okay? If you've got somebody who's very small, it only takes up this much of the chest, and the rest of this, of course, is abdomen, and then you put the shield on them because you guys are very conscientious about this. So we got the lead down here, PB. I think that's the designation for it. Okay? It's going to have a serious problem with this because you're going to create an additional bump. And you've created the additional bump over here. Okay? So now what we'll do is we'll have something like this going here. And it's not been programmed to ignore that. So you could end up something, for example, like this, and I'm using barium here. The bottom line is we've got a uptick on both sides here, and it's not ready for that. So what it'll end up doing is that it's not been programmed. It will start processing here. This is where the VOI1 will be. Okay? Now, on this other side here, nothing's changed, so this is where the VOI2 is going to be. So it's going to be in the right place. This one, on the other hand, not so much. Alright, so then you end up with a very, very poor confused computer, and you end up with an unsatisfactory image. Alright, okay, now, so histogram errors can occur, and it can occur for, I guess you'd say it's sort of like this umbrella type of issue that can happen because of segmentation errors, alright, exposure field pattern type of errors. Okay, they are both interrelated with one another, admittedly. Okay, histogram analysis can happen because you have things there that are not anticipated. And I want to point something out, guys. You can't always anticipate this either. Okay, if somebody, for example, you do a KUB and they have enough barium in there, basically to fill up an entire bag, and you didn't know that they had a barium enema the day before, how are you supposed to anticipate something like that? But once you see the image and you see what's going on, knowing the algorithm that you used, you should be able to change the algorithm perhaps and reprocess it. At least I hope. Okay? All right. Now, what happens too? Now, these are things that are automatically happening as the image data is coming in. There's two things going on. Okay? The data is looked at based on the template, which for now I'm going to call the lookup table. Okay, the data is also looked at in terms of the sheer volume of the data. Rephrase that. At the not the volume of the data, the intensity of the data, and how that actually works along the continuum of from bright to dark. Pretty clearly, what we want is something in the middle. Okay, so automatic rescaling is normalizing the data to a point where it's at a brightness that we like, okay? And here's the thing. Even if you put too much radiation in there or too little, the computer is going to make an attempt to normalize the data, make it at a normal brightness value that is acceptable to us. This is part of the way, essentially, you end up with images like this. We've gone from 5 to 640. I'll let you figure out what the differential is going here, but there's blessed little difference between any of it. What has happened is automatic rescaling has gone to work and shifted along the continuum from bright to dark and has consistently come to the same point. Didn't matter whether we use 5 mass, it didn't matter whether we use 640 mass, it has shifted it to the same point. That's pretty good software. Maybe not necessarily the best thing for the patient. All right, so what's kind of going on with this here? We have the histogram. Here's your distribution. Here's your data. Okay? But the data is on the low end of the continuum because you had an underexposure going here. Okay? In essence, what it does, it says, I want it over here. So it takes all of the data and it mathematically shifts it over there. It can do that. Here you have an evidence of overexposure, a high exposure. You still have the same data, okay? That hasn't changed, all right? You're shifting it along the continuum to optimum brightness and things like that. So what you're automatically rescaling, it's like we're going along this kind of continuum here of white to black, and we're putting it where we want it in the middle, okay? That's automatic rescaling. So when you look at it from here, this is just another way, and I'm sorry again, it working for me here, but it wasn't working in that room. I'm not sure what the deal is. Okay? Now, what they've done here is they've gone to work and they've given you 2 patterns. All right? There is the pattern here that's showing a good exposure, and then they're showing you, for example, an overexposure. So the proper exposure here is what it's anticipating. Then what it does is it mathematically maps everything out. Okay? And then it matches them. Now, this is just a graphical representation of precisely what I was just talking about. But ultimately what you're going to end up with is a good image, because it just basically maps things over. Because remember, it's math, it's numbers. You can add things to numbers, you can subtract things to numbers, or at least the computer can, okay? So it kind of works off from a respect like this, okay? Keep in mind that the grayscale that you get, okay, when you are talking about digital is a continuation, and that's why it's proportional, okay? So it's running along what for all intents and purposes is this straight line, okay? Where the gray here at one point, okay, ends up being what we have over here at another point, okay? Your original data, your process data. But you have the capacity to shift these things to match them too. So it is entirely possible, for example, if the image data that you had was too light, that you can bring it to this point anyway. You got the power, or at least the computer does. Okay? Now here's the other thing, let me clear this out. This gets back to the whole question of the sensitometry curve and everything too. Alright? This is what's actually potentially available, all of these grays. But we can't see them anyway. When we talked about, you could see about 50. Okay? So we really don't have any use for a dynamic range that has hundreds or thousands of grays. We want to see a subset of this. Okay? We don't want to see low contrast because we can't necessarily discriminate between them. Okay? So we're going to only pull a certain amount of the data out and display that. That's where the lookup tables come into play. Okay? In essence, lookup tables are driving your grayscale or your contrast, if you'd like. Okay? How is it doing it? Well, we still have, you see here, the ranges of grays on both sides. Okay? And we still have this potential continuum, but what we decide to do is to just utilize a limited portion of it. Okay? From here to here. These are the grays that we want displayed. Okay? This looks a lot like the sensitometry curve from film screen because that's what we like to look at. Now, does it have to look this way? No. You can make it look like something else. Okay? When we were looking at the histogram analysis, you notice one of the things that's happening is that the S-curve there could actually be changed as we went, for example, from high contrast to a lower contrast. The net result would be that the S had a much softer curve. Okay? Even to the point of being almost like this here. Okay? So if you want the ultimate in grayscale, then yeah, this is what you're talking about here. But that's not what we typically want to look at. Okay? So how does it do this? It's a math thing. In fact, all of these things are a math thing. Now, this picture here comes up frequently. It's in your book, for example. You can see here it's on these images that I purchased. They came from Perry Sproul's books. If you have a system that displays low contrast or has low contrast, in other words, it has the ability to tell the difference between something here and something here. And there's not a big difference between them, low contrast. Okay? Mathematically, it can say, okay, I got this, I got this. I'm going to make some changes. I'm going to make the ones that are lower, lower still. I'm going to make the ones that are a little bit higher. I'm going to really change them. Now, all of a sudden, mathematically, what we've done is we've grossly changed the difference between these. Now, instead of a low contrast image, we have a much higher contrast image. In essence, what we said is all 40s shall be risen to 90. All 30s shall be declined to 10. You can do that. That's what these algorithms do. Okay? There we go. Since I'm fully expecting these things are going to work. All right, take a look at a little bit what I was talking about here. The dynamic range of your image receptors, film screen versus digital. And by the way, when I'm talking about digital, I'm talking about CR and DR at this point. Okay? If you are looking at the analog version of things, okay, if you are down here at the low end, you're going to anticipate that you have very, very little value and you end up with an unexposed image. I'm talking about analog. Then you have where you really want it, and then of course you end up with overexposures. Okay, so the part that we really want is right from here to about here, okay, roughly speaking, okay? With digital, everything, remember, is totally stretched out, okay, because you have all of these potential grays. Now, owing to the fact that the automatic rescaling is occurring, okay, the lookup tables are working here and stuff. When you underexpose something, you can see what the result is. We've got an image here with reasonably decent brightness or density, if you'd like. Clearly can see that it's a hand X-ray, but it's very, very noisy. You simply don't have the data here. So it produces an image of sorts, but it's very noisy. It's really underexposed. Proper exposure, okay, which is in kind of that same general area of what we were looking at previously, gives you the best. But here's the interesting thing. Again, this relates to automatic rescaling, overexposure, and grossly overexposure, but this one in particular, you can still get away with it. All right, so that's the end of this, and I'm sorry, like I said, I can't edit out those areas there, but on the other hand, it's kind of cool.